Good morning, everyone, and welcome to day 5 Abstract Study Group. Good. So today's session 5, and we would like to touch on normal groups. Quotient groups. The first isomorphism theorem, and just literally introduce rings. Brief introduction. So we are on chapter 5, normal subgroups. So please have your notes at hand. You need to understand, we need to read. So definition: if H is a subgroup of a group G with operation star, then the left coset A star H of G is a subset A star H of G, where A star H is A star H, where H is an H. So we did this yesterday, yes? Brief revision. Definition 5.2. A subgroup H of G is called a normal subgroup or invariant subgroup or normal divisor of G if GH is equal to HG for all G and G. If H is normal in G, then we write H triangle pointing to the left, G. Nice. Now we can turn the page. No, I'm joking. So what does that mean? What does that mean? HG is what? From yesterday, HG is what? The right coset. And GH is what? The left coset. So, what does that middle line say there in terms of cosets? GH equal to HG is what? Means that the right coset is equal to the left coset. You all follow? So, in other words, we have a group G. Yes? We have a subgroup H. Yes? So we have a group G. You have some subgroup H. For H, if you take elements in G, you can have HG, and these are cosets. Everybody's okay? And these cosets partition G. Everybody's okay with this, right? If we were to represent it somehow, so they partition G, right? Not H, they partition G. So this could be H by A1, sorry, G1. This is just trying to get a representation, right? G2, we could have an next one here. H by G3. You all follow what's going on, right? Now, if the right coset is equal to the left coset, then we say that H, which is the subgroup, is normal in G. Yeah? Good. You'll understand the importance in a while. We're just building it up. Nice. So theorem 5.3. If H is a subgroup of G, then H is normal in G if and only if G inverse HG is in H. For all G in G and H in H. We want to spend some time going through this proof. One more time. So we have H is a subgroup of a group G, and the theorem is telling us that if H is normal, then G inverse HG is in H. Also, if G inverse HG is in H, then G is normal. So it's a biconditional. Yes, if and only if. Important theorem. So we will go through this proof. So let me write it on the board so we can break down the proof. Again, all the working is in the text. This is simply to get you all to understand the logic behind these steps. So we have H is normal in G. So H is a subgroup of G, then H is normal in G implies that G inverse HG is in H for all G in G and H in H. That's the first step. So this is, remember, it's if and only if, right? So we assume H is normal, then this happens. The second step is if this happens, then we can say that H is normal, right? So this is our proof. So we have the proof in the text, right? This is just to explain the logic behind it. So we know H is normal in G, so we assume H is normal in G. If H is normal in G, then we know by definition that the left coset is equal to the right coset. Everybody's okay with this? So we know this, so we've assumed this, and now we want to show this. Nice. Good. So we take an element in H. We need to start somewhere, right? So we take an element in H. So let H be in H. We call H, we call H1, doesn't matter. If H is in H, then HG would be in HG. Everybody's okay, right? Next. Now since HG equals to GH, we know this because we now assume this. We now assume. And this happens for all G in G. Then that means that HG is G by H0 for some H0 in H, which imply that if we take the inverse of G on the left hand side, so the inverse by the inverse, we get G inverse HG equals to HO, and HO is in H, so this is in H. That is more or less exactly the notes, right? Let's just go back to the definition of a normal subgroup. So a normal subgroup would be, we have HG equals to GH. Okay, I'm making an example. It's not going to be mathematically complete, so it's going to be wrong, but you'll understand where I'm coming from, right? So this is what? It's a set. Yes, so this is a set. And this is a set. Which means that if this set is equal to this set, then it's normal. Yeah? Good. Let's just say I had a set H, which was 1, 2, 3. AH would be A multiplied by all these elements, right? A by 1, A by 2, A by 3. Yes? Whereas HA would be 1 by A, 2 by A, 3 by A. You all follow? Now let's assume, again I'm just trying to get you all to understand, right? Assume that this was a multiplication and the operations were not commutative. So in other words, this could have been 4, I don't know, and this could have been 1, and this could have been 6, right? But in this case, this could have been 1, and this could have been 4, and this could have been 6. You all follow? Then the elements in AH are 4, 1, and 6, but the elements here are 1, 4, and 6, which means they're the same. But this first element was not necessarily this first element. So if I take an element, if I have G by H, that is equal to so if I take one element in G by H, which is say G by H1, and I have H by G, so this is my next set. Now I know that G by H1 has to be equal to, the G has to be the same, right? It's the same G. Has to be G by some HI from this set. So meaning that if this H was the first H, this is not necessarily the first H. So that is why here we have GH is HG is GHO for some HO in H, because we don't know which one of the H's is that H. It could be the ith one or the fifth one or the 10th one, we don't know. So, but we know it has to happen because both sets are equal. You all follow? Nice. So let's go back. So we know this happens because we are assuming that it is normal and we want to prove that it happens. We take an element H and H that is given. You have to take an element H and H. Call it what you want, H1, H2, H3. We just start with H and then we build. Let H be an H, then HG. So HG will be an HG. So this here is my specific H. Since HG is GH, so HG is GH, then I know HG is GHO for some HO. You all see it? One more time. I take an element HG in HG. That is given. H has to be from H and G is G. G is not changing, yes? But because I know this here is equal to G first and then H, then I know this is in GH, yes? But because they are equal, then it has to be equal to G by some H in H. But you don't know what that H is, so we call it HO. Nice. So now we have this. So you have G, so I have HG equals to GHO for some HO and H. Take inverses from G because G is a group and G is in G. Yes, so inverses exist. So we get inverse here, so we get G inverse HG is H, HO. And we know HO is in H, yes, because it was some HO. So this is in H and this is equal to this, therefore this is in H. Right, so we prove the first part. Right, so the second part, we are going with this part now. So conversely, we suppose, so we assume that G inverse HG is the element of H for all G in G and for all H in H. So I'm just going to pause a bit. So for example, right? So this proof here says that G inverse HG is an H. Yes? Everybody's okay? In other books, you will see GH, G inverse in H instead. Which is exactly the same thing. Why? Because G is in G and G is a group, so G equals to G inverse. Well, G and G inverse exists. So if G is G1 inverse, then this would be G1 inverse, all inverse H, G1 inverse. The inverse of the inverse, this is G1 H, G1 inverse. And at the end of the day, G1 is still in G, so it's the same theorem. You all follow? Right. So we assume this, and what is it that we want to show? We want to show this happens, and this happens if HG equals to GH. Again, it doesn't matter if I have GH equals to H, right? It's the exact same thing. I just flip the equal signs, right? Equality, right? So this is standard. If I want to show this, what do I do? Subset. It's a set. So let HG be in HG. So I'm using this one. Yes? Now HG is equal to E by HG. Yeah? And E is G inverse, which is HG. And we group this. And we know this is an H. So if it's an H, we could call it H2. So now we have GH2, and this is in GH. Because G is G and H is an H, so it's in G, capital H. You all follow? So the trick was the identity here, yes? Which means that we took the element in here, HG. HG is a subset of GH. And we'll have to do the converse side, yes? So try the converse side, converse. Also conversely, let what? We want an element in GH, yes? GH, one element of GH. Now this here was not necessary, right? It was not necessary to have this as H2. But for you all to see it properly, that's why I did it, right? So take a minute and just work through this. And my last line would be that my last line would be is an element of HG. Right? So you want to get that to be an element of HG. would be GH1E, which is GH1, G inverse G, which is GH1, G inverse by G, which is G inverse H1 by G inverse G, and this is of the form element inverse H element. Y'all see it? So this here is a H3, which is H3 by G, which is an H by G. It's nice, huh? It's nice. You understand, right? It's just the form, eh? It's just the form G inverse. So whatever element it is the inverse of that by an element in H by the element itself, yes? So in this case here, my element was G inverse. So I have G inverse, I have an element in H, and I have the inverse of the element. Yeah. So therefore, we've shown so therefore we've shown that GH is a subset of HG. Hence the result follows, right? Hence the result follows. You'll have the notes, right? I mean, you'll have the book. Best. Everybody's okay. Nice. Term 5.4. Every subgroup of an abelian group is normal. This one is more or less straightforward. This is probably the easiest proof ever. Let H be a subgroup of an abelian group. Since H is a subgroup of an abelian group, then H is also abelian, which means that you can interchange the elements, which means that so you take an element GH in GH, but since G is abelian, then GH is HG, and HG will be in capital HG, and you can do the converse as well, yes? Therefore, you're showing that both sets are equal. Hence, H is normal. Example 5.5, singleton E. You all remember that from yesterday? The element with only the E in it, singleton. Singleton E and G are normal subgroups of G. In other words, any group is normal in itself, yes? Which makes sense, right? Because everything will be in itself. Right, so that brings the, I wouldn't say a close, but a nice little closure of quotient group of normal subgroups. Let G be a group of all integers under addition. So we have G, which is integers under addition, and H be the set of integers divisible by 5. Then H is a subgroup of G under addition. Furthermore, H is normal in G, and the decomposition of G into right and distinct cosets leaves the following equivalence classes. So I would put H, you all see how example 5.6 starts with H? I would just put that in the next line. So I would rewrite H, so just so you all would understand. So H1 would be all the elements in G, which is Z, such that 5 divides x minus 1. I would put H0, or H is x in G, such that 5 divides x minus 0. Yes? So give me some elements of H0. Anybody? 5, 10, 15, and we have the negative ones as well, yes? Give me some examples, some numbers, some elements in each one. Y'all seen it? So this means 5 divides x minus 1, which means it's k, so x is 5k plus 1. So 6, 11, y'all going on, right? So and this one will be what? The first one on the negative side will be one k is minus 1, minus 4, minus what? Everybody's good? Yeah? Nice. So we have H2, H3, H4, and H5 would be what? H5 would be H0, yes? Same thing, yes? Nice. So this is the remainder when we divide a number by 5. If we get 0, then it belongs to H1, yes? This is the remainder when we divide by 5. If we get 1, it belongs to H1, yes? This is the remainder when we divide by 5, we get 2, is H2. You all follow, right? So, and you'll understand that these are all the remainders we could possibly get, either 0, 1, 2, 3, or 4, right? Remainder of 5 is not a remainder, it's remainder 0, yes? So, I have Z. Remember, Z is negative 3, negative 2, negative 1, 0, 1, 2, 3. And these numbers, if we write it, we would have seen it better. So this is 5, this was 6. The next one will go in 7, 8, 9, and 10 would have repeated here. Y'all see that? So this, just give me some numbers here. So this is 1, 2, 3, comma, negative 8. So we have 1, where's 0? We have 0. We'll get 0 is at the bottom, right? We have 1, we have 2, we have 3, we have 4, we have 5 and 0, yes? So we have 2, we have 3, we have 4, we have 5, right? We have 6, we have 7, we have 8, we have 9, we have 10, right? We have 11, 12, 13, 14, 15, 16. You all follow what's going on, right? Yeah. So these 6 partition Z. Everything's good on the positive side and on the negative side, yes? So the relation modulo n, in this case n is 5, partition Z is it is an equivalence relation. So the equivalence classes, would be H0, H1, H2, H3, and H4. Y'all follow? And this here would be Z5. So equivalent, this is Z modulo 5, right? So that is the operation. I didn't define it. I just give the example, yeah? YouTube video, you're good to go. But you all understand what's going on, right? So this is the remainder. When you divide, this is the remainder of 0, yes? Which is the equivalence class of 0. Yeah? Equivalence class of 0. This is also the equivalence class of 1. This is the equivalence class of 2. Equivalence class of 3. And equivalence class of 4. You all follow? Which is Z5. Yes? So the elements in Z5 are, now sometimes, because we understand we are in Z5, instead of writing the equivalence class all the time, because we understand that we're dealing with remainders and the equivalence class is generated by those remainders, we could just write 1, 2, 3, 4 to mean exactly this. Y'all okay? If we don't write the square brackets, it's fine, but if you write it is proper. So this set, along with addition, forms a group. Yeah? And the identity would be what? What would the identity for this group would be? 0 addition. You understand, right? Because if we have one element 1 and we add 0, remember 0 is really 5, right? Or we could add literally 0. Yeah, we could add 0. Or we could add 5. If we add 5 to 1, we get 6, which is still in H1. You follow? So the identity is 0, yes? And the inverse of A would be B such that A and B are co-prime. Co-prime means no common factor except 1. But I don't want to go into this because the goal is just to introduce it, and none of the examples that I have linked with this right now. It was mainly to just go through this. Y'all met this before or not? Barely? Slightly? Yes. 0, 1, 2, 3, 4. 0, yeah, thanks. Zn has n elements, yes? Just to finish this, right? Because what would be the inverse of 1? So the inverse of 0 is the inverse of 0. To finish off this example, the inverse of 0 is the inverse of the identity is the identity. The inverse of 1 is you want to add to get 5 because when you divide by 5 you get 0. The inverse of 1 is 4. Yeah? The inverse of 2 is 3. Y'all okay? And the inverse of 3 is 2, the inverse of 4 is 1. 1 and 4 co-prime, 2 and 3 co-prime. Everybody's good? Nice. Y'all understand, right? I'll just give one quick example. So an element in H2 is what? 7, yes? H2 had an element 7, yes? And an element in H3 was 8. So we add this and we get 15. And 15 is 3 by 5 plus 0, which is the identity. I took an element in H2. In H2, and an element in H2 is 7. And I took an element in H3, which was 8. And the inverse of H2 equals to H3. So if I add them, I'm going to get the identity. So I want to show if I add 3 plus 2, I'm going to get 0. So when you add 7 and 8, you get 15, and 15 is really 0. Yes? Alright, so we are going on to fact 5.7 now. A relation is well defined if every object has a unique element f. So i.e., f is well defined if a equals to b implies f of a equal to f of b. It is not one-to-one. That is the converse of one-to-one. Well defined. So one-to-one is what? Anybody remembers what one-to-one is? If it's one thing, you all must know one-to-one by now. I mean, forget that you do that. You do that since form 5, right? So remember one-to-one was if f of a equals to f of b implies a equals to b. This is one-to-one, yes? So well defined is if a equal to b, then f of a equal to f of b. You all might say it's straightforward, right? Anybody can come up with a function that's not well defined? So if a equal to b, a plus 1 is b plus 1, a plus 1 over 2 is b plus 1 over 2. But if we take the square root, we get plus or minus. Plus or minus. So this plus could be equal to this negative, so it's not one-to-one. It's not well defined, you all follow? I didn't have to add, I could have just taken it at the start, but yeah. The square root function is not well defined, right? Because for an a, you could have two values. Square root of 4 is 2, negative 2, so it's not well defined, right? Right, here we are on theorem 5.8. If G is normal, then the set of cosets G slash N equals to G, so G is an element in G, and N is the subgroup of G that is normal. That's why we have N for normal, yes? So you have a group G, you have a next group N that is a subgroup of G, and N is normal, and we form this new group which is denoted by G slash N, and the elements in those groups are cosets with G and N for all G in G, and we define a new operation G, so N G1 star N G2 is N G1 G2, and we claim that this new set under this new operation star is a group. You follow? So one more time. I know, don't worry. We have a group N, we have a group G, yes? Day one we have a group G. Then we realize that we have a subgroup. So we can have a subgroup that we generally call H. So H is a normal H is a subgroup. But in addition to H being a subgroup, if H is normal, meaning that this happens, then we could form a set G. Now because H is normal, we could call this N, so normal. we write this set as G slash N, and the elements in this set are defined by, we take the set that is normal and an element in G, which is the group, and multiply it here. And this is a coset. And this happens for G in G. So this here is a group in which the elements I was going to write elements, right? The short form, and the elements are cosets, right? You all follow? And we define the multiplication such that ng1, ng2 star is n by g1, g2. That's how we define the multiplication. So in other words, we have a new group formed from G in which the elements are cosets themselves, and the multiplication is defined by one coset multiplied by a next coset is actually the coset formed by the product of the two elements. Yes? You understand the levels now, right? We ain't reached the isomorphism theorem yet. Just now we reach it. Just now. So we have to prove that this with this new multiplication is a group. That's what we have to do. So we have to do that. What we do is we define, first we need to show that this new multiplication is well defined. That's basic. We need to show well defined, and then we go through the properties of a group. So for well defined, we need to show that if A equal to B, then FA equal to FB. Yes? Why we need to show it well defined? Being well defined ensures that elements are unique. Meaning that if you take A and you take F of A, you will get, say, B all the time. It's not that you can take A and you get F of A sometime and you get and you get C sometime and you get D sometime. So it needs to be well defined for maths to work. Yeah? If you want to get extrapolated a little bit more, if it's not well defined, then inverses and identity will not be unique, which will just collapse everything else. Yeah? Just the first is not bad. Once you all understood what we did before, which you all did, this proof here is not bad at all. So we need to take two elements. So we need to take two elements in the group. Sorry, A and a B in my set, and then I need to show F of A equals to F of B. Elements in my set are what? Elements in my set are this, yes? They look like this. Yes? So I have NG1 and I have NG2. But NG1 is NH1. This might be the hardest thing to explain. This is an element in my set, yes? So I take my group and I multiply by element in G. So what I'm saying is that this answer that I get is equivalent to n multiplied by some other element h. I don't care what h is, it's just the next element. You all follow? Same thing here. So my two elements are G1 and G2, but I know NG1 must give me something, and NG2 must give me something. This is just the something. Nice. Class. Yes. So we are on the third line here. Then by definition of star, NG1, NG2 is NG1, G2. Yes? That's given. Now G1 is an NG1. So G1 is an NG1. But NG1 is NH1. Yes? Therefore, G1, so G1, because it's an NH1, we don't know which N it is that gives us the G1. So we call that N1H1. We can't change the H1 because the H1 was from here, yes? You follow? So that's how we get G1, and this is for some N1 in N. We do the same thing for G2. So we know G2 would be N2H2 for some N2 in N. Yes? Therefore, G1 by G2 is G1 by G2. Everybody's good so far? Again, it's literally in the notes, right? It's in the notes. So we call this 1. Now, G1, G2 by H1, H2 inverse. This is G1, G2 by H2 inverse, H1 inverse. And we replace G1 and G2, which would be N1, H1, N2, H2, H2 inverse, H1 inverse, which is N1, H1, N2, H2, H2 inverse, H1, which is N1, H1, N2, H1 inverse. So we have this here now, and we know that N is normal in G. So what does normal in G mean? You remember? So if H is normal in G, what does that mean? G inverse HG element of H, right? So the normal one is in the middle, yes? So N is normal in G. So it would be this, yes? And so this could be, we could rewrite this as what? HGH, yeah, same thing. It's an element of, right? So it'll be an element of this multiplied by element of this, because it's closed, then it'll be in G. So we can call that big thing an N, and that would be an N. Everybody's okay? So one more time. N is the normal group, right? So this here is an N. So if you wanted, you had N1, and this here could have been N3, right? And N3 would be in N, since N is normal in G. And this is a product of two elements that are in N. and N is a group. So it will be an N. Now all of that is just to say that G1, G2 by H1, H2 inverse is in N. Yes? If this is an N, then we know that N by this will be equal to N, because it's an element in the group, right? And the group is closed, yes? N is a group, which would imply that N of G1, G2 equals to, you take the inverses of this, right? Would be N of H1, H2. Which means we've shown that we've shown well defined. So we've now shown we've taken two elements, and the image after we apply the binary operation to those elements, G1, G2 is equal to H1, H2, and H1, H2. You all follow? Nice. That's just the first part, right? We have closure, associativity, inverses, and identity, which are more or less straightforward. So closure.
How is N, G1, H1, H2 inverse equal to N? I get all your map of N and your sum is square H1.
Because N is a normal subgroup, right? So if you have a normal subgroup and you multiply, remember, groups are closed. Yeah. So if you have to take an element from the group and you multiply it, then you'll still be about the same group. Look at it as cosets, right? They are cosets. If you have G is a group, and you have H is a subgroup, and you take an element A in H, then AH will be HA will be H. This was one of the theorems we did before. But in this case, this here is equal to my element, my A. Yeah, you understand? Yeah. So we really took the bare bones. So we took things from that we needed and we just wrote it in so we could build on it. Right? Closure. So we take two elements in the factor group, right? So NG1, because NG1 is an element in G1 and NG2 is an element in G2. You all follow? The product would be NG1, NG2, which is NG1, G2. And we know that is equal to, now G1 by G2 will be an element. Say G. Yes? So that's how we get that equal to NG. And NG would be in G on N. You all can imagine if somebody from literature come in this class. Watching at these things. When I was in undergrad, I used to have real disputes. I wouldn't say disputes or argument with my friends in lit. Yeah, because I mean, it's just so nice to give them like a math paper with alpha, beta, and gamma and tell them read and Well, alpha because they don't know, right? Anyhow, associativity follows from the associativity of the operation on G. So that is the line for associativity. That is just straightforward. We multiply, we switch the brackets, we show that they're equal. Nothing to talk about there. Yes? Next line, it is clear that N is the identity element of G/N. You understand that? If you're gonna see it, just put N by E. And you know E does nothing to it, right? So it just gets absorbed. Inverses NG by NG inverse is NGG inverse, which is NG inverse G. Which means that the inverse of NG is NG inverse. You all follow? Yeah? Everybody's good? Now we come to the big part. We almost come to the big part. Theorem 5.9. The group that we've now proven G on N is called the quotient group or factor group of G by N. This is important. You can't mix up the two, right? It has of the bigger group by the smaller group. Yeah? Of G by N. I thought about it for a while to see how I could get you all to remember this name, factor group, and I came up with this. So if I have 30, the factors of 30 are what? 2 by 3 by 5, yes? Everybody's okay? We can say 1, right? 1, well. So let's just say this is my group G, and this, this is just me thinking, you won't find this in a book anywhere, right? This is just trying to get you all to understand, right? If G was say 30, then I could have broken down this into 2, and this could have been 3, and this area could have been 5. So we take a big group and we break them down into the factors of, but in our case, it's not numbers. These are cosets. Right, so we factorize the group into the cosets. You understand? And then we add a new operation, multiplication. Yeah? Good. Right, so the group G/N is called the quotient group or factor group of G by N. Everybody's okay with this? Exercise, the last 2 exercises we would not do, because I want to go into the last thing before we go for the break. So now we are here, we are on page 46, theorem 5.12, the first isomorphism theorem. Open brackets. This is a big theorem, major theorem, huge. Do you get the point yet? Let F be a mapping from G to H. Let that mapping be a homomorphism between 2 groups. So in other words, we have 2 groups with kernel K. Do you remember the kernel? Then the kernel is normal in G. That was our theorem before that we didn't prove. So we know the kernel is normal. That's standard, right? Whenever you have a mapping, whenever you have a homomorphism, the kernel of that homomorphism is always normal in the domain. Yes? Then K is normal in G, and the factor group of G by the kernel is isomorphic to H. You understand that? I'll try to explain it once or twice, and then we'll go to the break. We will not go through an example today. It needs to be soaked in a bit. Right? So we have a group G, yes? Well done. Beautiful. We have a next group H. We do not know anything about, well, we know H is a group, right? H is not necessarily a subgroup, right? H is just a next group. We have a group G and we have a group H. We form a mapping F from G to H. We don't know what that mapping means. But associated with each mapping, so we form a mapping from G to H that is a homomorphism. Remember, homomorphism F of AB is F of A, F of B, where this is the operation in H, and I'll just put a star here. This is the operation in G. You all okay? So we form a homomorphism F from G to H. Associated with that homomorphism are elements such that F of these elements gives me the identity in H. Right? All these such elements form a set Xi such that, well, this happens, right? All these elements are in G, yes? Such that F of Xi equals to EH. This is called the kernel of F, or the kernel of the homomorphism. Yes? So now the kernel is a set, yes? So now we come back with G, and we have this set here, and we multiply elements in G by the set to get cosets. And these cosets here, this set that in which elements are cosets is isomorphic to H. Yeah. You all saw the levels there? We will not do the proof, because the proof, in order to prove this is isomorphic, to prove something isomorphic, you have to create a next homomorphism and prove it's one-to-one and one-to. But there's the proof. I could put the video up on YouTube. So for the course, definitely. I mean, you must know the proof. You're watching the first isomorphism theorem, open brackets. This is a big theorem. Obviously, you need to know the proof. I mean, it's a basic theorem. You can't come out of algebra course and not say that you know the first isomorphism theorem or the proof. You have, basic. you have to know. How you could not know it? I know, but I'm emphasizing the point. You follow? The good thing about knowing and understanding the proof of the first isomorphism theorem is that it helps with understanding the second isomorphism theorem and the third isomorphism theorem. And wait, there's something called a correspondence theorem, which is also very important. But for all intents and purposes, we will stop at the first isomorphism theorem.
What is the third isomorphism theorem?
Normally it's called 1, 2, 3. So that is standard proof, standard text, you'll get it. It's just to spend some time with it and understand it. And I think you all know enough to understand it, because the proofs that we went through today and the understanding behind those proofs, this is just nothing. All this says is we just need to show isomorphism, that's it. And we've done yesterday, we've done isomorphism, which are the three things: homomorphism, one-to-one, and onto. You're following? Good.